Let's think about a trip from Nicholson, Georgia, all the way down to beautiful Panama City Beach, Florida. It's going to take us about 6.5 hours, and it's going to be a 365-mile drive. And if we were asked to find the average velocity or rate or speed at which you drive down there, how would you go about doing that? Well, you'd use your middle school algebra skills, of course. In middle school, you had this formula. It was distance equals rate times time. I feel like there was even some sort of like weird pyramid that y'all drew. And I could write that several different ways. I could say, rate equals distance over time. I could also solve for time. I could say time is distance over rate. And if we think about our trip, if it's 6.5 hours from Nicholson, Georgia, all the way down to Panama City, and it's 365 miles, I could, if I'm looking for my average velocity or my rate of getting down there, I could take 365 and divide it by 6.5 hours, and that would give me miles per hour. When I do that, my average velocity is 56.15 miles per hour. So what does that actually mean? Well, that means on average, for that trip, we traveled at 56 point, I think it was 15 miles per hour. And we wanted to find our average rate from Nicholson to Panama City. But what if we left early in the morning and we could go a little bit faster on 85 because there wasn't any traffic, we didn't have to stop too much? Or what if we got caught in traffic in Columbus or Phoenix City and we had to pull over at the beautiful Dothan Wendy's to grab some lunch as we went with the rest of Southeast America down to the beautiful Riviera? We need to rewrite it in a little bit more complicated way. We had a really simplistic version of this formula, and just to reiterate, it was rate equals distance over time. And a little bit more sophisticatedly, since we're living in the suburbs of Nicholson, we can write that as change in distance over change in time. And you may have seen that as like delta D delta T, something like that. So we've got our sophisticated way. If we were gonna kind of write that algebraically, the change in distance would be, I'd plug that maybe where we end up at from where we started. So that would be the distance. And then I would find the change in time, my x values. And, I wrote down here an even fancier way that people describe this as the average velocity over a given time interval. So time interval is going to be our x's down here, can be defined as the change in position or displacement up top over the elapsed time. So we could also write this as displacement over time. So let's look at our first problem. A ball is thrown vertically into the air from ground level, which is kind of weird thinking about starting at the ground level, throwing it upward, with an initial velocity of 15 meters per second. The ball's height at time t is that. So our height, this is our function of height. How far does the ball travel during the time interval 1 to 3? So just a second ago, we were talking about displacement, and that's all I need to do here. I need to find h of 3 and subtract h of 1. Okay, so what I'm going to do is I'm going to take 3 and I'm going to plug it into this, and then I'm going to subtract 1 plugged into all that stuff. So I'm going to rewrite it like this. I'm going to say 15 times 3 minus 4.9, 3 squared, all that, minus 15 times 1 minus 4.9, 1 squared. So all I did was take 3, plug it up there, subtract all that. Notice parentheses right there. Got to subtract all that stuff. Punch that in your calculator and you get negative 9.2 meters. And that just means that if you graph this thing, you can get on Desmos and look at this thing, but that means it's just coming down 9.2 meters. What is the ball's average velocity over the time interval 1 to 3? So average velocity, remember, we got the whole thing. So this was displacement or distance kind of. It's not exactly the same things, but displacement over time. So average velocity, we're going to take the displacement and put it over the time. So what we're going to have is the thing we just had up here, minus 4.9, oops, wrong way, parentheses, 3 squared. That goes that way. Minus 15 times 1 minus 4.91 squared. And then all that over the difference in time. So my time interval is 3 to 1, 3 minus 1. Punch that into your calculator and it would give you negative 4.6 meters per second. So moving in a downward direction at negative 0.4 or at 4.6 meters per second. So we're coming back down on average from time 1 to time 3. On average, we're coming down 4.6 meters per second. Okay, let's flip it over and let's keep looking at some of these. All right, at the top it says a particle moves along a line and its position, P of t. And remember just a second ago I was talking about height was what we were getting, but this is the position in meters after time t seconds is given by the following table. So we got this particle, whatever the heck that is. It's moving along this line and its position in meters after so many seconds is measured right here. So at time 0, it's 3 meters, okay? So it's on a straight line and it's traveled 3 meters. So describe the motion of the particle between 0 and 1.3 seconds. I don't really like this motion. I want to call that the displacement. I think that's kind of a better word right there. What's happening to this particle as the time is moving on? Well, it starts at 3 meters. Okay, we're starting at 3 meters, and then it's moving up 4.2 meters, keeps moving up, and then it's coming back down, and then it goes back up, goes back up, goes back up. So if we start at 3 meters, let's say that it goes forward or up, whatever you want to say, until the time is 0.65 seconds. Okay, and so when we're at 0.65 seconds, we're at 8.8 meters, and then we move backwards a little bit. So let's say at t equals 0.9, particle has moved backwards, or you could say down, depending on what you set up there. Okay, so now we're at 0.9 seconds, and then it's moving back to 8, 9, 9.5. So let's just say moves forward to 1.3 seconds. Okay, so we want to find the average velocity of this thing over here. And really all we're practicing here is just reading it from a chart. So instead of on this side, we were taking the function and plugging it in, this is reading it from a chart. So what I would do, let's write it like this. Let's start writing it like this. P of 0.9 minus P of 0.2 over 0.9 minus 0.2. Okay, so that's just a fancy way of writing it like this. We had our displacement over time. So displacement over time. And if we look at P of 0.9, I'm going to come over here to my chart. And where time is 0.9, P of t is 7.6. The other one was 0.2. P of t is 4.2. So I'm going to write it as 7.6 minus 4.2. So that's my displacement over my change in time, 0.9 minus 0.2. And you can plug that in your calculator and it will give you 4.85 meters per second. Okay. How about you pause the video real quick and try that other one? Okay, so you should have written it as P of 0.9 minus P of 0.65. And when we come over here to the chart, we can see that, well, first we got to write our time, sorry. So this would be 0.9 minus 0.65. So when I come to the chart for 0.9, I see 7.6. And then for 0.65 is 8.8. So let's write that. We've got 7.6 minus 8.8 over 0.9 minus 0.65. And that's going to be a negative number, negative 4.8 meters per second. So if I'm looking at that makes sense. From 0.65 to 0.9, it's moving backwards. Therefore, I have a negative velocity here. Next example, I got acrophobia here. All right, we're on top of acrophobia. If you don't know what the heck acrophobia is, it's a really tall ride and you get dropped and you get scared. It's 200 feet up there. When we're dropped, our height can be modeled by h of t equals negative 16t squared plus 200. Find the average velocity from 0 to 2.5 seconds. All right, from 0 to 2.5 seconds. I need my displacement, so that would be h of 2.5 minus h of 0 over 2.5 minus 0. All right, and I'm going to show this on the first one. So I need to plug in all this stuff. So h of 2.5 would be negative 16, 2.5 squared plus 200 minus negative 16, 0 squared plus 200, all over 2.5 minus 0. Plug that into your calculator. You're going to get negative 40, okay, feet per second. Okay, try that next one. Push pause, try that next one. You probably wrote it all out, and if you did, then it would look something like this, except you just have 2.5 right there and then 1.5 right there. I'm going to write it just like this, and we can start writing it like this just to kind of save some space. Okay, and we can leave it like that. You can punch it in your calculator yourself, and we'll skip this step writing this part. And we're going to end up with negative 64 feet per second on this one. All right, let's slide it over to this next one. We've got, oh man, this is a good one. All right, Jimmy is upset Tommy done stepped foot on Jimmy's land again, hunting squirrels. Tommy ought to know better. As Tommy's running away, Jimmy gets his Red Ryder carbon action 200-shot range model air rifle out and sends up a warning shot because apparently Tommy ain't no good at reading the no trespassing signs Jimmy posted up earlier in the week with his buddy, Old Lou. The BB is fired at 160 meters per second. The height of the BB can be modeled with the following function. Okay, so the height of the BB after we shoot it can be modeled at this. Find the average velocity. I'm going to change this. Let's make this from 1 to 2 seconds. Because the BB gun won't be in the air for 20 seconds. Let's change this one while we're here. Let's make this 0.1 seconds to 0.5. All right, so we're going to find the average velocity from 1 to 2 seconds of this BB that has been shot up in the air by Jimmy, who is upset at Tommy, who has been hunting squirrels on his land again. All right, find the average velocity. I've got h of 2 minus h of 1 over 2 minus 1. That's my average velocity function right there. So I'm going to subtract, get the displacement up top, elapsed time down here, punch that into my calculator, and I'm going to get, I think it's going to be 145.3 meters per second. Be able to punch that in your calculator. Don't just copy this crap down and expect to know how to do it. Make sure that you can punch that in your calculator and get 145.3. Okay, next one. So, you know, if you shoot it at time 0, 1 to 2 seconds, that's pretty close to right when the shot's fired. 0.1 to 0.5, that's even closer to when the shot was fired. So just like if it was fired at 160 meters per second, on average from 1 to 2 seconds, it had slowed down a little bit. It's at 145. From 0.1 to 0.5, I expect it to be faster than this. Slower than 160 from when it was first shot, but faster than later on, okay? Because this is closer to the time 0. So let's plug this in. I got h of 0.5 minus h of 0.1 over 0.5 minus 0.1. And if you plug all that into your calculator, you're going to get 157.06 meters per second. Okay, so this is really close to that 160 because it was right after it was shot. So on average, from 0.1 seconds to 0.5 seconds, it's going to be 157 meters per second. All right, last example. A golf ball is hit toward the cup from a distance of 50 feet. Assume the distance from the ball to the cup is given by this function. How far did the ball travel from 2 to 4 seconds? I don't know if the ball is getting putted from 50 feet or chipped or what the deal is, but it's starting at 50 feet and it's getting closer down here to 0. And then it looks like at 5 seconds, it goes past the hole a little bit. So maybe, I don't know, 2-3 feet past the hole. So, all right, how far did the ball travel from 2 to 4 seconds? How far did the ball travel? That's going to be displacement. That's not average velocity. That's just the displacement thing. So I'm going to say from 2 to 4 seconds, h of 4 minus h of 2. And that's all we'll write on there. So, you know, just to kind of reiterate this, we're going to plug 4 in right here and then subtract plugging 2 in. So I'm going to write all this out this time. So plug 4. 2, I don't know why I put a parentheses there, but I did. Minus 20, I guess that's why I did. 20 times 4 plus 50 minus 2 times 2 squared minus 20 times 2 plus 50. And when you punch all that into your calculator, you will get negative 16 feet per second. So what is that negative 16 feet? It's actually not even that. It's just negative 16 feet. So how far did the ball travel? We just did the displacement. How far did the ball travel from 2 to 4 seconds? Right there. Well, it looks like it traveled, 16 feet from right there. All right, let's look over here. So instead of just displacement, we're going to look at average velocity over here. Find the average velocity. So between 2 and 3 seconds, I'm going to have to say, let's say d, since it said it over there. D of 3 minus d of 2 over 3 minus 2. And your average velocity for this one is negative 10 feet. And this one is feet per second. This is average velocity. So it's traveling away from you at 10 feet per second on average from 2 to 3 seconds. Okay, from 2 to 3 seconds on average, it's traveling away from you 10 feet. If I were to plug these in over here, so 2 to 2.5 seconds. I'm going to get negative 11 feet per second. Okay, so it's traveling a little bit quicker. You know, that's a little bit smaller time frame right there. So we're getting really close to maybe just seeing what it would look like at 2 seconds. And that's definitely right here. So from 2 to 3 seconds, it was negative 10 feet per second. And then we're looking at a little bit smaller snapshot from 2 to 2.5. And here we're looking at a really small snapshot. What's the average speed from 2 to 2.1? So I would just say d of 2.01 minus d of 2 over 2.01 minus 2. And that would give me negative 11.98 feet per second. So that's really close to using the word instantaneous, or like right at a very specific time, how fast is that golf ball traveling away from you? It's going almost 12 feet per second.